Yeah, thank you, Tunde. I'll show you how to deploy your Python model into production and actually convert you from a data scientist into a data engineer. I don't know how many data scientists are here. Can we have a raise of hands? Oh, that's like 3/4. So a lot of data engineers after this talk, I guess. There's no difference. Oh, that's a good company, I guess. Basically, my intro is developing a model is actually half the battle, right? You still need to put it in production. But apparently, it's like an overlooked battle because I have this chart here. I even made them into log axis. So a lot of people are searching for data scientists. A lot of people are searching for machine learning. Nobody's searching for productionizing any of those. It doesn't happen, like 13,000 hits. But I think it's an overlooked battle because, like in the previous presentation, you'll only see the benefits of a model once it's deployed in production. So without it, it's only just an exercise. So a little bit about me. I have a PhD in parallel computing from TU Delft. I'm a data hacker at GDD, which is like in between. But basically, I drink a lot of coffee while waiting for this Pandas thing to compute. I don't know why you guys find this interesting. I certainly don't, but apparently it's a thing for data scientists. So a little bit about my employer, Go Driven, also sponsor of this conference. We're part of the Xibia group, blah, 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 data scientist. And if you buy some of us, you should buy 6, apparently, according to Holden. Same applies for GDD. So let's start. So basically, I did this project at a client, and I'm going to describe the process we deployed there. And the process is like this. It's a lot of steps. It's quite complicated, but I'll mention all of those in the next few slides. But before we continue, any questions up to now? One question, yes. Okay, so there's a data scientist in the back who builds models who should not go into production. I'll come back to that at the end of the presentation. I think it's a valid point. There is quite a gap between data scientists and data engineers, and depending on scale, I think it might not be the best choice to put a data science model written by a data scientist into production, but it depends on scale. But I'll come back to that in the end of the presentation. One more question. Previous slide. One more even. Uh-oh. Is it the spelling mistake?
It's a spelling mistake.
Oh, it's a spelling mistake. Okay, no. Okay. Maybe it's not that bad. Okay. But Google should have autocorrected it. Bad data science. Okay. So GitLab. One of our core components is just where you house your code, right? Apparently, GitLab now it unifies issues, code reviews, CI, CD into a single UI. But back when we did the project, it didn't do the CI and the CD. So give me some slack because we used Jenkins as well for the CI, CD. So what we did in our project is we had a separate repository for each model. Each project or each data science model had its separate repository. And then when we had feature branches, so if a new improvement needed to be done on the model, you would create a feature branch. A data scientist would implement the feature, do some unit testing maybe even. Hardly ever happened, but it happened. And then when the feature was ready, it would be merged into master. And our aim of this project was that once it was merged into master, we would actually get an automatic deployment to dev. Maybe not production, but let's start with dev. So we use Jenkins as well. So Jenkins is like it's a big line. But more importantly, since Jenkins 2, you have this thing called pipelines as code. And this basically means that you have a file describing how the CI, CD part of your deployment will happen. Does everybody know what CI, CD is, by the way? Should I elaborate? Okay, maybe I should elaborate. Okay, CI is continuous integration. So it's like building a new version, packaging it with all the dependencies, making it ready for CD, continuous deployment. So once you make a small change to your model, it will automatically be deployed to production. CI, packaging it, CD, deploying it. Yes? Okay, so I guess it depends on your definition of continuous. Continuous could be like if you do really small feature increments, you could deploy multiple times a day, and if you deploy more than I don't know X, you call it continuous instead of like every release. Is that a good answer? Okay, so this is another good question. You don't know how good is your feature. I think that okay, it should maybe be part of your deployment pipeline or CI pipeline to test if it doesn't like radically change the behavior of your model. But it's also something you should do after, like in the monitoring of your model. Like, does the CTR drop like crazy? Okay, maybe we should roll back. But that's more monitoring, I think, than the CI. So for Jenkins, we create a separate pipeline for each model. So remember, the pipeline states which steps should be undertaken to integrate and deploy. And Jenkins is actually monitoring the master branch. So once we merge this feature, the master branch changes, we start building a new packaging, a new version. So, and we run a Jenkins file specific to an environment. It's a bit difficult, but I'll come back to that at the end of the presentation. Basically, you have different environments, dev, test, accept, and production. The Jenkins build changes a bit between those. So this is a Jenkins file example. So you see the different stages. You have some code in between in an actual deployment, but basically with the different stages, you get this thing. So you see the different green blocks, and the green blocks represent that everything went okay within one of those stages. So let's say this green block represents this Git checkout, this 30-second block is the Docker prepare, and this one is the Docker build. And this is really nice because you can monitor how long it takes to do the continuous integration. So if over time you see like, I don't know, packaging takes a lot more time or there's some problem there, you can actually monitor this change in the Jenkins UI because of the different stages. Everybody still okay? Okay. So then Docker. So why do we use Docker and not like VM, the typical Python virtual environments? So what we do is a Docker container allows us to package all the dependencies inside a container. And a container is like a lightweight virtual machine, more or less. So probably the experts don't agree, but that's what I call it. And the benefit of this is that it packages all your dependencies. So not only the Python dependencies, but also like specific versions of your Linux subsystem and like everything. Everything is captured in this one container. So this removes the dependency hell, right? If it runs somewhere, it will run everywhere, depending on if the host is Windows or it will run everywhere. But still, in contrast to VMs, it's still lightweight. So a lot of the downsides of a VM, big memory usage or the containers itself being really big, that's removed. It's still quite lightweight in Docker. So what we need to do for our project is create a Docker file for each model. In this Docker file, we make sure that we run some unit tests to make sure that we don't build a broken container. So you build your container, you run some unit tests, and then if the unit tests don't pass, we stop building the container. And what we did is we installed Miniconda, some dependencies, and then the unit tests. So a really small example of a Docker file snippet. Okay, so what we do here is we have this environment YAML file. It's like a normal Anaconda environment dependency file. And what we did is we have a single step a single Docker step, which first installs all kinds of dependencies, installs Miniconda, installs the environment, cleans a lot of installation, like PyC files, PyO files, which are not really needed, then removes all the GCC and all this stuff in one go. And why do we do this? So Docker has this concept of layers. Yeah? So a Docker container is like an onion. You have a core layer and then one outside. And so this means that you can only add stuff. If I would split this operation into separate run operations, the actual size would only increase. Like this cleaning I do here, it would never help. Because basically it's a command like, okay, and now remove this stuff. But the stuff is also actually still there because it's in a layer which is below it. Yeah, so you can only add stuff. So basically it would add one layer stating remove this. And there's techniques. You could squash the final Docker container. So basically squashing all the layers into one. But the problem with this squashing is that you can't reuse layers between containers. So that's also a bad practice, let's say. So that's why you get these crazy code blobs in a typical Docker file. Okay, so now we have our Docker container. Yeah, we know how to build those. So then why did we choose Kubernetes? So Kubernetes is an open source, basically container manager. In Kubernetes you have multiple worker nodes, so multiple machines. And on those machines we're going to run containers. And we're going to run multiple containers per machine, depending on its size or how, the load, etc. And the nice thing of Kubernetes is that it actually manages this process. So if we're in a big project and we're doing microservices now, everybody's doing microservices, you can just throw all these containers to Kubernetes and it will make sure that the load is nicely distributed amongst all those worker nodes. It will monitor all those different containers. If one breaks down, it will restart it somewhere else. A lot of the hassle is taken out. A lot of the monitoring you have to do is taken out. So for Kubernetes, create a separate deployment file. It's like a descriptor telling Kubernetes how to launch and monitor this container. And in this descriptor deployment file, it will actually define how many CPUs and memory you actually need and how to monitor its liveliness and its readiness. So those are two important concepts. So liveliness basically means, is the container still alive, right? Is there still like a reply to a certain HTTP call? If it's not, Kubernetes kills the container and spawns it again somewhere else. And then there's this concept of readiness. And basically readiness means that if you reply with a 200 on that request, your model running inside this container is actually able to serve requests. So it has an active connection to the database. I don't know, it has finished loading the model itself. So if it didn't finish loading the model, like at boot up, it doesn't make any sense to kill it already because starting it somewhere else will not improve the situation, right? You just have to wait a bit more. Two concepts. So even nicer code example here. Actually, this template is much bigger in practice, but basically this is a snippet of your Kubernetes example. So I'll give you a general overview. So you have a model name, which is defined here. You define how many replicas you want for a particular container. So in this case, we define 2. And then there's this thing called rolling update, which states max unavailable is 0. So basically, what this means is that if I push a new version, max unavailable is 0. So it will wait until the new version is ready. So the readiness probe says OK, before killing the old version. So you'll have like near instant switch over to a new version without any downtime. So then going down, we have a pointer to an image, which is basically the name of the image we just created in the Docker step. There's some ports defined, how to find the liveness probe and the readiness probe. That's somewhere here, I guess. And then you can actually pass some arguments, like how to connect to your database. And you can actually get some secrets, like passwords to connect to the database. And those secrets are actually managed by Kubernetes. So you don't have to check them into Git or something like this. They're just managed by Kubernetes. And then finally, let's do finally, and then I'll come to you. So then finally, you'll specify the limits. How much memory, how much CPU this container can take. Yes?
Where would you want maximum available not to be 0?
I guess if you don't really care about this switching over. Yeah, it's a good question actually. It's not a default setting. So by default, it will just, if you deploy a new version, it will just kill the old ones and then you'll have downtime.
So maximum available is the number of pods that can be available, right? So if your replicas is 25 and you say maximum available is 5, then we'll always have 20.
Yeah, okay. So I'll repeat it for everybody else. If you have much more replicas, it might make sense to have like max unavailable is like 10. If your replicas is like 20 or 5, or that you have a minimum amount or a maximum amount which can be unavailable while deploying a new version. So the final step we had to do is monitoring. So we installed Heapster to monitor containers. So Heapster will actually monitor the execution nodes themselves. So we have these execution nodes in Kubernetes. These have CPUs and memory as well. So we monitor their CPU usage using Heapster. And then finally, we use Elk to collect the logs of each container. So we have that's the nice thing of microservices. You deploy your container somewhere, you have no clue where, but you still need access to the logs. So you need to be able to, you need to set up something which is collecting those logs from your containers, pushing them somewhere centralized to be able to actually do debugging still. Because debugging sometimes is actually quite a nice feature to have. Maybe not if there's JVM stack traces, but still. And then from the Elk stack, we actually use Kibana to create some dashboards, like how many requests your model is doing, the runtime, how many errors it encountered, that sort of stuff. Okay, so summarizing. As a data scientist, in order to become a data engineer, you need to do this. Create a GitLab project, a Jenkins project, multiple Django files, Docker file, multiple Kubernetes deployment files, some HTTP endpoints. You need to log in the correct format. Should be something any data scientist can do, right? It's not like building a model. It's not science, just executing those steps. So what we actually did is we created a library/framework. And this library basically did all of that for the data scientist. So what we did is the core essence of it was generating most of those templates. So do you need more memory? Do you need more CPU? Right? Some of the models, they're just really simple. You don't need more than one CPU. If it was a bit more complex, then maybe you just specify 2 or 4, I don't know, something like this. Same goes with memory, right? Not all data science models will actually consume a lot of memory. Some will. You could fill it in here. And then what we did besides that is create a custom Flask app. Flask is a HTTP server. I think most of you are familiar with it. And this would allow you to expose this data science model over HTTP calls, REST calls. And it works from the premise that your model method would get a data frame in, and it should return a data frame. Everybody knows Pandas data frame, I hope. Okay, so that's basically the common format. So within the predict function, you could do whatever you would like, but as long as the output was a data frame. Our Flask app also had predefined health endpoints. So it would always, on the liveness probe, it would always return everything is okay. And on the readiness probe, it would return okay if basically the init was passed. So if you actually started. Fred is still here? I think so. So additionally, we created a custom JSON logger. So basically it's an extension of the logging framework to make it log in JSON format. Actually, it turns out the JSON logging in the console is completely unreadable, but Elk, our logging capturing tool, could actually parse it really easily because it's JSON. They have some standards for that. So this JSON logger allows us to capture and parse basically the logs in Elastic really easily. Then we had a shared Docker file, and in this Docker file we install the base dependencies like Pandas, Scikit, NumPy, some others, like the default, basically PyData stack. Let's call it that. And we implemented some connectors to databases and message bus. And basically this was because, we used Cassandra. And Cassandra, there are Python connectors to it, but you have to be careful, let's say. So by us implementing those connectors, the data engineers would take away this careful part from the data scientist. So everybody was happy. So then the resulting workflow. So we would fit the model as a data scientist, write a small wrapper to make it compatible with our Flask API thing, create a requirements.txt file. If you needed more dependencies than the default dependencies we install already, then you run this wizard to generate all the template files like the Kubernetes, Jenkins, everything. You push it to GitLab. GitLab would automatically pick up like, hey, I have this new repository with a Jenkins file in there, and it will automatically deploy it to dev. Second time, bit less work to do. You merge the feature into master, Jenkins would pick it up, and you wait, basically. Any question up to now? Still no. Must be a really clear presentation. So, so after merge to master, we use dtab. So basically we have 4 separate environments: dev, test, accept, and production. And we would automatically deploy to dev. Right? Dev is the environment which may break, no problems there. Everybody's still more or less happy if you break dev. Once everybody was happy with a particular dev container or a dev release, we would upgrade it to test. That was a more stable environment. Still integration test with all the different components were done. And then after test came accept and production. So basically the nice thing of this Kubernetes is that we build the container for dev, and once we think at least that a container is stable enough to be upgraded to test, you just pick the same container and you push it to test. So there's no changes. You don't rebuild it. There's nothing there. Everything else, like connecting to a different database or connecting to using a different, loading the model from somewhere else, that's all done through configuration parameters passed through Kubernetes, basically. So it's really nice from Docker. Yeah.
So you said after merge to master, does it mean you do this after? You don't do this on pull request, you do this on before?
Okay, so this you're right. Okay, so this was we built a container after pushing to merging to master. Yeah, we did. I think it was a choice I made, but in theory you could build containers while pushing to any branch, right? But then I think the problem with building containers for any branch is that it becomes a bit unclear which version is now deployed to dev, right? Because if you commit something to a branch, it would be pushed to dev. And if you're working with 2 people on one project, you have 2 branches, then like the last one wins. So nobody knows anymore which version is deployed. Now we also had like a small dashboard which stated which version was deployed, blah, blah, blah. So that could help. But in the end, for simplicity reasons, I chose to only deploy master.
But it means you can have unstable masters. Because is the acceptance of merging must happen after you use the master than unstable?
Okay, I'll come back to that.
It's not possible just to apply to the Docker version. That was the same as the master, so you would always know what is the version of your development environment.
Yeah, sure. Docker tags, you have to be a bit careful about that. Because the problem with Docker tags or reusing Docker tags is that you can't really know anymore which version is deployed. Because if you have multiple repositories, has my container synced from one repository to the other or not? So if I check out master and it's a different repository, you don't really know if I'm checking out the last master or the one before. Or
Your Git repository is also tagged, and it's the same tag as the Docker image.
yeah, okay, but then you don't really see. You could prepend it. Okay, but then in the end, I think it still boils down to more or less the same problem I said. It was a personal choice for me to deploy master. It's one which could be debatable. Yeah, sure.
You can have two tags, one as a version and
Yeah.
the other as a latest, and
Yeah.
then use the name of the container without the latest, or so that which is the one that is
Yeah.
using.
Okay. So again, I think there's some debate around how you would deploy. I think multiple branches could be okay, but at the time I chose to only deploy master. So then this is more or less the same image as I started with, but now with the different deployments, right? And the Docker registry. So we start with the code in GitLab. Jenkins does the checkout and builds the container. The result of the Jenkins build is a Docker container, which is pushed to the Docker registry. And then we have separate Jenkins jobs which fire to deploy a version to the different DTAP environments. So there's dev, test, accept, and production. Any questions about this? Yeah. Okay, so in this project we had a 2-week cycle, let's say, release cycle, just sprints. And yeah, then how long would it take from GitLab to production? It depends, right? On the Thursday before going to production, this would be 1 day. Or half an hour. But yeah, if it's the first commit you do, it takes 2 weeks. No, there's nothing keeping you from doing it continuously. That's a good point. In essence, what we did is we had one Jenkins job doing this part, checking out code, pushing to the Docker registry. And then we automatically fire the dev deployment. You could fire more. You could also say, okay, I don't need test and accept, let's do dev, works, push, production. That's how you want to organize your whole team, let's say. It ties into my almost last slide, which is lessons learned. So I think automatic deployment to dev is a really nice thing. Also, depending on your team, also. But I think it's some oversight still. So I think in the end, it's still, depending on this, it's still, some data scientists get more oversight than others. Which makes sense, right? Everybody started with a different education. I know that scientists come from an analytical background. They learn a lot about statistics. I know less about statistics, a bit more about programming. So without the oversight, it sometimes leads to somewhat messier repositories. It doesn't have to be necessarily the case, but it is something you need to take into account. And especially if you optimize everything away like this. It's really easy for basically anybody to do a deployment to production because it's just streamlined. Then again, I think investing in the framework or our library paid out big time. We had a more uniform code base, data frame in, data frame out. That was basically the API we had. And also new features in the framework would improve all the data science models. So instead of having to fix a certain problem at, 10 different data science models, you could just fix it in the framework, update the pointers to all the data science models, and then done. So that really helped a lot. And then the final remark, which is more or less like one of the earliest questions we had here. How you still need to monitor the performance of your models. So what we did is we had some regression tests for each model to have like a baseline performance. But if the performance degradation is more subtle, like the click-through rate degrades only a couple %, this unit test was not designed to capture that. So you still need to think about how am I going to monitor your model once it's been deployed to production. There's still a big thing there, and it's not captured in this talk. Okay, so that's it. Any questions?